Greetings, I'm Louis Little and wish to continue the discussion of the elementary wave theory. In the introductory video, it was indicated that quantum mechanics and the elementary wave theory will in general make the same predictions. And the question might then arise, well, how can one distinguish them? Can one do an experiment that would show one theory rather than the other to be correct? One would have to find an experiment where they made differing predictions. And at least for the static sort of experiments that we talked about in that video, where none of the components are in motion, there is no way to distinguish them. They would always make the same prediction. However, there is one experiment that I have thought of that might be performed where there are differing predictions. Before describing that, I'd like to express a little reluctance I have to present such an experiment, because according to my way of thinking, the experiments distinguishing elementary waves and quantum mechanics have already been done. Any of the experiments that lead to particles being two places at once, or time going backwards, or what have you, these are contradictions. An experiment or theory that leads to contradictions is refuted by that. And by a contradiction now, I don't mean just some abstract logical relation of symbols. I'm speaking of real things. A real particle can't be two places at once. You say it's in one place, but it's not in that place. It's in the other place, but it's not there either. It's somehow neither and both. This is a contradiction, and as such already refutes quantum mechanics. And I'm concerned that if I came up with another experiment showing that quantum mechanics leads to a contradiction, or can only be accounted for with some new contradiction, instead of it refuting quantum mechanics, someone would come up with some new kind of weirdness, and I'd become famous for inventing a new weirdness, instead of confirming the correctness of the elementary wave theory. But with that in mind, let me describe the theory, the experiment, and hopefully someone will perform it. It's simply a takeoff on the double slit experiment. And what I have here is a drawing of that experiment. If you'll ignore screen B and C for a moment, it just pictures a source of particles going through two slits and forming a pattern. Now, according to quantum mechanics, if screen A were not present and you looked on screen B, you'd see the same pattern. And the same is true of the elementary wave theory. Wherever the screen was located, you'd see a similar pattern. It would be a little wider if you looked further away, but it would be basically the same pattern. What happens, however, I'll bring up another picture here. This shows the experiment as it would look with solid screen A, and again, you'd see the same sort of pattern on B and C. These lines are intended to represent the path of the particles that form the highest peaks on the screen. Of course, there are particles going in all directions, but just drawing in the ones that correspond to where the highest peaks would be. According to both theories, wherever this screen is located, these peaks would correspond to where the trajectories met at that point on the screen. And you can see the trajectories be a little different if the screen is at a different distance. That'll become clearer with the next drawing. The idea is to do an experiment where you start out with an opaque screen at screen A location, so that it would be just like the previous experiment, previous picture. But you use a material that can be switched electronically or rapidly in some way between opaque, and transparent. So you leave it opaque. According to the elementary wave theory, the waves would be coming from the points on the screen at this location, going back through the slits to the source, and stimulating the emission of particles. And when the particles leave the slits, they'd be following trajectories corresponding to the location of this screen. Now, once those particles have gone through the slits and started traveling across, if you change that screen to transparent, they're already following the same trajectories. And if there's a second screen behind here, the trajectories would take them to points where the line from one slit does not coincide with the line from the other slit. So these lines where most particles follow would occur apart from each other, and there would be no pattern appearing on the back screen, according to the elementary wave theory. Quantum mechanics, again, would say you'd see the same pattern no matter where the screen was located. The idea would be to make this transparent just for the briefest instant, so that only particles that had gone through the slits following waves coming from screen A, only those would go through and strike the second screen. And one could even confirm this further. That if you had a screen back at location C, back here, you would see a pattern, but it would not be the same pattern as you'd expect from quantum mechanics. Instead of the peaks being locations like this, they'd be in between. Quantum mechanics would have predicted a maximum in the middle of these points, and instead you get one at different points. That confirms that you haven't just lost the coherence by having this screen turn to transparent from opaque. So the two theories make different predictions about what you'd see. You'd have to rapidly turn this opaque, transparent, just for the briefest instant to capture the particles that had already gone through, and then make it opaque again before there was time for waves from the back screen to make it through and generate particles following those waves. So you'd make it transparent just for a brief time and then opaque again, and do this repetitively at high speed so that you'd be able to see the patterns. And I submit that would distinguish the two theories. Hopefully some ingenious person will do this experiment. It's not as easy as it might seem. One needs a very rapid switching rate. One probably needs a very long distance, but I believe it is doable.